We are very glad to have today Professor Tilman Pfau from University of Stuttgart. Tilman got his PhD and did some of his postdoc work and habilitation with Jürgen Mlinek in Constance at the time in the early 1990s, where the manipulation of atoms and atomic interferometry was a hot topic. And after that, he spent some time as a postdoc at École Normale with Michel Leduc and Christophe Salomon, and also a postdoc with Wolfgang Ketterle at MIT. And then he came back to Germany to get a position of professor in Stuttgart. And during the last 10 years, he has been doing very beautiful experiments on cold Rydberg atoms. And he will talk about these experiments today. So I'm very glad to give you the floor for your talk.
Thank you very much. And thank you, Serge, for this invitation. It's a great honor for me to speak here. During my postdoc time, I have been listening to these lectures, of course, on a weekly basis. And it's a really special event for me to speak on this stage. So maybe we can dim the light a little bit. Is this like here? Okay. So I'm going to talk about experiments that we are doing with Rydberg electrons and how those electrons are interacting with ground state atoms. And the subtitle is From Two to Few to Many-Body Physics. And during the talk, I want to walk you through basically these various aspects of this interaction. So the two and few body aspect is basically what is nowadays called Rydberg chemistry or ultra-cold Rydberg chemistry, where we are talking about novel binding mechanisms between atoms, one being a Rydberg atom, the other one being a ground state atom, sometimes called trilobite molecules, and they have become quite famous because they are giving you nice pictures like this one, or there is another nice picture here in an advertisement post that I found in a mall in Boulder, actually, in the US. And we are going to learn during the talk what these giant molecules are all about. But then also we will make our way and one step further and ask the question, how can a single electron interact with many bodies in a Bose-Einstein condensate, for example, and couple to phonon excitations in such a many-body system. And of course, this is a very interesting scenario that you, of course, know, for example, in the context of Cooper pair formation in solid-state physics. Now, before I start, I want to give credit to my group that is working on cold Rydberg atoms. We are working on many different aspects. I'm not talking about all of them today. And I want to, in particular, mention the two senior people involved. One is Robert Löw, a permanent staff member in my group. And the other one is Sebastian Hofferbert, who has a young researcher group in my institute. And he is working on Rydberg quantum optics and has recently actually realized a single photon transistor based on this very strong Rydberg interaction. And I'm not going to talk about this aspect today. I also want to mention that we, over the years, had a strong collaboration with various theory groups. And as we go through the talk, every once in a while, I will mention some of these names that have been very crucial for us to understand what we are actually doing. Now, during the talk, actually, I want to go a little bit back in history to the 30s even. You see a number of faces here. You can already think about who are these faces. Before I then come to another characteristic or important step in the development that was introduced by Chris Green here, namely formulating this novel binding mechanism between ground state atom and Rydberg atoms. And then I show you some experiments that we have done to investigate those trilobite molecules, those Rydberg molecules, and will then make continuous progress to put more and more atoms into a Rydberg orbit eventually having up to 30,000 atoms inside a Rydberg orbit, and that's a many-body system that is actually coupling to this individual Rydberg electron in the end. And if I have time in the end, I want to highlight another activity in my group where we are not only using those nice and strongly interacting Rydberg systems in cold atoms, but where we are also more and more discovering that all these phenomena can actually also be applied in thermal vapor cells, which is actually very interesting for possible applications. All right, so let's go back in history and to this picture. And by now you have recognized, of course, some of the important figures here that in the year 1934 have worked on Rydberg spectroscopy before actually all of them went into nuclear physics. And this is the so-called Group of Rome. Of course, you have recognized Enrico Fermi, but there's also Emilio Segre and Eduardo Amaldi, who have been performing, in my view, very crucial experiment on precision spectroscopy at the time on the Rydberg series that we have just seen in the course this morning. So what those two guys were doing, Amaldi and Segre, was taking a precision measurement device of the time, which was just a high dispersion prism, and looking at fluorescence spectra, Rydberg spectra, on a photographic plate. And what they then did is they looked at this fluorescence spectra in the presence of some buffer gas and investigated pressure shifts. And there was a big surprise in these measurements that I'm going to describe to you right now. Up here you see a print that they published in this paper, which is written in Italian, but you can guess what this is about. It's elevated termini, so Rydberg states in alkali atoms, and they are investigating the effect of pressure shift. Okay. So how do they do this? Well, they take sodium. You can read it here. Yes? It's sodium. It's a 35 to 8p line here on this photographic plate. And they measure this in the presence of a buffer gas, the pressure of which they are changing. Or in other words, they change the density of these buffer gas atoms. Here you have a hydrogen buffer gas at, say, 10 to the 18 per cubic centimeter, and then you increase this by a factor of 50 or so to 5 times 10 to the 19 per cubic centimeter. So that's our huge densities, and actually almost corresponding to ambient pressures at the time. Okay. So what they observe is, if you look closer, is that the lines are actually changed due to this buffer gas, and they are shifted and broadened. And the surprising thing in this example was that this shift is actually going to the blue side. Okay. And so they did some systematic measurements, because this was unexpected. Because if you now think, okay, I have a buffer gas of polarizable atoms, then this should basically shield the charge, and there should only be redshifts. And so they were very puzzled by these blue shifted lines and did systematic measurements as a function of density here, and this is the shift. And they found that for hydrogen, for example, there is a blue shift. For helium, there's also a blue shift. For argon, there was a red shift. So even the sign was different for different buffer gases. And some atoms or buffer gases, like nitrogen molecules here, did not show a shift at all. Now, if you do the classic calculation that I just described, you end up with this, so classical electrostatic problem, you end up with this straight line here, and this could clearly not even quantitatively explain even the redshifted lines. So there was a quest for some theoretical work that was in the same year then published by Enrico Fermi to explain what is going on. And I want to basically go through this argument with you. If you take a charge like this Rydberg electron and let it interact with a ground state atom, in our case it's going to be a rubidium atom which is polarizable in the ground state, okay? So there's a ground state polarizable object. Then the interaction between those two objects is given by the Stark effect, basically. So you have a polarizability alpha times E squared. And the electric field of this charge you can, of course, write down. So you get a field that goes like 1 over r squared. So the effective potential between those two bodies is a 1 over r to the 4th power potential, just being proportional to the polarizability alpha of this rubidium atom in this example, okay? And it's an attractive interaction, of course, and that's why it has this negative sign. Now, what Fermi realized is that when the electron is interacting with the buffer gas, most of the time it is actually very slow, okay? And therefore, you have to treat the scattering from this potential in a quantum mechanical way. You cannot just go and argue classically here, okay? So what he already at that time realized, and I think it's the first time in the history of physics, is that this real potential can be replaced by a pseudo-potential that has a zero range, like a delta function, and the prefactor of this pseudo-potential is the scattering length. And in his paper, also in 1934, he shows this picture which immediately tells you what is the meaning of this scattering length. Namely, if you have the relative coordinate r here, and you think about a de Broglie wave coming here in the scattering problem, then if it gets attracted towards the polarizable particle, then there might be some wiggles here, but that's not important basically for the asymptotic behavior. The only thing that is important is basically the shift of this asymptote with respect to the origin. In this example, this shift is actually negative, corresponding to a negative scattering length. Okay. So this is what we nowadays also teach about the meaning of the scattering length, and it's already contained in this paper by Fermi here. Now, if you ask yourself, what is then the range of interaction, so the length scale associated with this potential, then there is an easy calculation to be done, namely just setting equal kinetic energy and potential energy. Or in other words, you are asking yourself, where is the first node of this wave function, up to some factor maybe. Yes? So we just have basically the kinetic energy expressed in terms of this length scale r star. So that's the reduced mass here, and that's the length scale r star, and set it equal to the potential energy here in SI units. And then you solve this for r star, and you see that this r star is basically just proportional to the reduced mass mu and its square root and the polarizability alpha. And if you go to atomic units, of course, all these things are set to 1, and so what you need to calculate is just the square root of the polarizability in atomic units. And this number for rubidium is very well known, and you calculate the square root, and you get in atomic units, so in Bohr radii, the range of interaction for this polarism, for this interaction. And this number turns out to be 18 Bohr radii. So that's a very small length scale, much smaller than the scattering length that you are, for example, used to if you think about two cold atoms colliding. Okay. And we will come back to that length scale in a minute. So basically, if you have a normal atom, then this scattering length should be on the order of this length of this range of interaction, right? But of course, if you have bound states and so on, then there can be resonances, there can be sign changes in this scattering length, and the value can change. And that was basically the explanation of Fermi for the finding of Amaldi and Segre of all these different density shifts with different signs and slopes. So then basically the interpretation of this data was just to say that there is an interaction between the Rydberg electron and this background gas atoms, interaction energy U, which is proportional to the scattering length, which can have positive or negative sign, times the density of the background gas atoms. And that's what they see. They see a linear dependence in the density here. Okay. Good. Actually, interestingly enough, all of these people in the year after, in 1935, went into nuclear physics and applied these concepts, exactly the same concepts, partial wave decomposition and so on, to neutron scattering, slow neutrons scattering, and we all know what came out of these studies then. Okay, but the whole thing started in Rydberg spectroscopy. I show you another historic plot, actually from a German group in Rostock from the same year. They had these measurements also done, very similar to the work of Amaldi and Segre, and measure here as a function of the principal quantum number now, again, this pressure shift at a constant pressure, 1 atmosphere here. And they see, again, that helium shifts to the violet, so to the blue. Neon has no effect. Basically, argon has a redshift. And you see that this shift is actually above a certain principal quantum number, independent of the quantum number. Okay? Does not depend on the principal quantum number, does not depend on the size of the Rydberg atom. And they only published this paper after they have read Fermi's explanation and immediately understood sort of their results that before that they could not interpret, basically. Okay. But they also talk about very slow, sehr langsame electrons, so very slow electrons that are in this quantum regime. Okay. Good, so far the history sort of this problem where you have a Rydberg electron that is basically trapped by an ionic core. So there's a strong interaction, of course, between those two charges. And a ground state atom that is predominantly interacting with the Rydberg electron. Already here you can see that the interaction of this ground state atom with the ionic core is negligible, because I've shown you that basically this pseudo potential goes like 1 over the mass. And so the light particle basically has by far the stronger interaction energy than a very heavy charge, basically. Okay. So we can safely neglect the interaction between the ground state atom and the ionic core. But now you can ask the opposite question. I mean, we have discussed now what is the effect of this buffer gas ground state atom on the spectroscopy of these Rydberg electrons. We can ask the opposite question and ask, what is the effect on the ground state atom if I put a Rydberg atom? Okay. And this brings me to this crucial plot that I will show several times as I go through the talk, which compares just various length scales that we have in Rydberg physics. As a function of principal quantum number, we have the size of the Rydberg atom, and you have already heard that this, of course, scales with n squared. So then there's another, so that's the size of the electron orbit. Then there's another length scale, of course, in a dense medium, and that is just the interparticle spacing, so the third root of the density. So if you go up here, then this mean particle spacing becomes smaller and smaller. Now, this red line basically tells you where is the borderline between those two length scales. Yes? If you are in the upper right corner, then basically the mean particle spacing is much smaller than the size of the Rydberg atom, which means that you are going to have one, two, few, or many ground state atoms of your dense medium inside your Rydberg orbit. Now, you have already heard about this strong interaction between two Rydberg atoms, and there's another length scale associated with this that is, of course, always larger than the size of the Rydberg atom, and that is the so-called blockade radius, which means that if you excite one Rydberg atom and you want to excite another one with a narrowband laser, then you have to go a large distance away. And that effect is due to this very strong van der Waals interaction that scales with the 11th power of the principal quantum number. And if you plot now this blockade radius and compare it basically to the other two length scales, then you come up with this blue line here. So all this white area is dominated by blockade physics, where you have many atoms inside the blockade radius, but still only few atoms or less than one atoms on average inside the Rydberg orbit. And the low density case is this blue corner down here, where basically mean particle spacing is the largest length scale of all. All right, so we are going to start with our experiments in density regimes in a thermal cold cloud of 10 to the 12, principal quantum numbers of like 30 or 40, and during the talk make our way to principal quantum numbers of around 100 or so. We are going to cross this border. And and ultimately, we are going even to principal quantum numbers of 200, and go to a Bose-Einstein condensate where we have a density of 10 to the 14. So we are going to go very deep into this many-body regime in the upper right corner. So if you come back to this initial question, what is the effect of this Rydberg electron on the ground state atom? Then Chris Green and co-workers came up with the answer, namely that there should be a bound state due to exactly the same interaction that Fermi basically introduced. Okay. So if we come back to Fermi's argument, you remember this formula that this pressure shift is proportional to the density of background gas atoms times the scattering length. Now, if you ask the opposite question, how does the electron affect the atom? Well, the formula is more or less the same. You just replace the atomic density here by the electron density. Now, the electron density, because this is just the Rydberg wave function. We have seen very nice pictures this morning. This is just the example of an S state. So basically, the electron density is just the square of the Rydberg wave function, which you know. So if you then basically multiply it, say, by a negative scattering length, then you end up with a basically molecular potential that you can quantize. You can come up with vibrational states that you can spectroscopically investigate. And basically, this is what we have started to do in 2009 in the first paper by two-photon excitation in a dense medium. Just the way that Serge introduced this optical excitation and subsequent field ionization, we can just measure how many of those objects are we exciting. Okay, and I'm going to show you a spectrum or a series of spectra for principal quantum numbers 35, 36, 37, just to see how it typically looks like. Yes, you have an atomic line at 0 frequency, which is very large, and then on the red side, so you find some bound states at lower energy due to the attractive interaction with a negative scattering length. And now if you basically do your if you solve your Schrödinger problem in this potential, you can very nicely attribute all the measured spectroscopic lines, these black lines here, and associate them with your measured spectrum. So you see that these lines here are all lines that belong to a dimer of this bound molecule, one ground state atom with one Rydberg atom. But when we did this analysis, there was always this outermost peak here, which appeared always at exactly twice the binding energy of the largest dimer peak, which we could not explain with a dimer picture. And so we were forced basically to conclude that this line, which has exactly twice the binding energy, corresponds not to a dimer, it corresponds to a trimer line, which means that we not only have one ground state atom inside the S state orbit here, but we have two. And as the length scale, this range of interaction is very short, 18 Bohr radii, on the scale of the Rydberg wave function, this is a very small length scale, the interaction is just additive. So this ground state atom and this ground state atom don't see each other, okay? So that means if you trap two ground state atoms in the electron orbit, you will just observe twice the binding energy. Okay, so these are all these lines, and actually here's a more recent spectrum where you see again the dimer line, but then if you blow up the trimer line, you again see a lot of substructure that we can discuss if you want later on. But then you even see a tetramer line, which is sort of 3 ground state atoms trapped inside this Rydberg orbit. And if you have some confidence or so, then basically here you see yet another one coming up. So then there are 4 atoms basically inside. And now you see where we are heading. Basically, we put 1, 2, 3, 4, many in the end inside the Rydberg orbit. Okay. Now, if we look at the binding energy itself, maybe we look at it here. This is the scale in megahertz. For this 43S, the binding energy is on the order of 5 megahertz, easily resolvable in our spectroscopy technique here. If you ask yourself, how does this binding energy scale with the principal quantum number, then there is an easy answer. Yes, you increase the size of the Rydberg atom, you increase the volume of the Rydberg atom. Therefore, you reduce the electron density just by this factor. Now, the volume increases with n to the 6, so the binding energy should just go down with n to the minus 6. Okay, so this is the molecular potential. That's the electron density, and that goes down like n to the minus 6. So now if we go to higher principal quantum number, for example 62 now, again we see the dimer, trimer, and this tetramer here. If we go to 71, we see the dimer, trimer, tetramer. If you have some phase, you see the pentamer, and so on. So you see more and more of those polymers coming up, but you also see that the binding energy gets smaller and smaller. Yes, this is only a spectrum of 1 megahertz width here. So the binding energy of this dimer is only 200 kilohertz, okay, at 71. And of course, at some point, we are just losing resolution, right? So this is now going even higher. So at 80, we cannot resolve these individual molecular lines anymore. And if we go up to 100 or 111 here, we basically just see a line that is broadened and shifted. And now if you go back to the Amaldi-Segret result, then this is exactly what you expect. It should not depend on the principal quantum number. This mean shift, basically the center of gravity of all those spectra should be a constant, which it is here. That's this yellow line, or it's in this plot, it's this line here, which is just proportional to the scattering length and the density. Okay. In this case, it's 10 to the 12 density. It's still a thermal cloud. And here I show you this n to the 6 scaling, or the measured n to the 6 scaling for the dimer, trimer, and so on. Okay. Actually, up here you see that these molecules are actually large, yes, that they are micrometers in size. Okay. And you see, of course, that you get more and more such particles coming into the Rydberg orbit, and that explains why it does not depend on the principal quantum number, right? I told you that the binding energy goes like n to the minus 6, but of course the number of atoms inside this orbit goes with n to the 6, so the whole effect just cancelled and you get a constant mean shift here, which is on the order of a few hundred kilohertz here. Now what happens if you are going up in density now? Now we go from a thermal cloud just to a condensate. Okay. Here's a spectrum 121s in a condensate. 2 orders of magnitude larger density, 2 orders of magnitude larger density shift, just like Amaldi-Segret. And you see this is 20 megahertz. Yes? So on the red side, you see a shift, a density shift basically of 20 megahertz. You actually see a thermal cloud that has a lower density here around 0, and that is the condensate part of the spectrum. And you can see this if you are basically heating the condensate by just putting more and more Rydberg atoms. It's going to heat it. Then you see that the BEC peak basically vanishes, so from here to here to here. The cloud gets hotter and hotter, and ultimately you have basically completely dissolved the Bose-Einstein condensate and heated it into a thermal peak only. That's the red spectrum here. Okay. Good. So this tells you now that actually if you put Rydberg atoms in a condensate, it heats the condensate. So there is sort of some mechanical coupling or some coupling between this electron and the whole condensate. And we were asking ourselves, what exactly is going on? And this is where the blockade physics comes in, because if you think about these very large principal quantum numbers, then basically the Rydberg blockade becomes also very extreme. And I just want to show you this again. I mean, this is the van der Waals coefficient C6 that scales with the 11th power, telling you that the blockade radius becomes even larger than the size of the whole condensate at these principal quantum numbers, which means that you are able to isolate a single Rydberg atom inside a condensate. Okay. And that's nice to do quantitative analysis of the measurements later on. Okay, so if we are back to our plot here, we have now started at 10 to the 12 in the thermal cloud and have made our way to the BEC. And above a principal quantum number of around 100 or so, the blockade radius is even larger than the whole condensate, which isolates a single Rydberg atom and lets us investigate this many-body physics quite nicely. So this is now coming to our BEC work. I show you first only two different Rydberg states, 110s and 202s. The blue one is a small one, which has a 1.2 micrometer radius. It's a small one for us, which is smaller than the size of the condensate itself. Yes. Our condensate has a radial Thomas Fermi radius of about 5 micrometers, so 1 micrometer is much smaller than that. On the other hand, if we go to 202s, the radius of the Rydberg atom becomes comparable to this Thomas Fermi radius, at least in the transverse direction. And we are going to see some finite size effects in the end, because now over the size of the whole Rydberg atom, we have an inhomogeneous density distribution. And if you calculate how many atoms are inside this Rydberg orbit now, then for this 110s, it's about 700. So we are not talking about trimers or so anymore. It's really many bodies, or in this case, even 30,000 atoms. And then we went to our BEC apparatus and just did spectroscopy again. So what we measure this time as a function of the tuning is how many atoms out of the condensate do we lose as a function of frequency. And the zero is just the reference spectrum in the thermal cloud again. And you see for the 110s, we see a loss feature in the condensate, which again has a shift of about 10 megahertz, which is our old friend, the density shift, of course, in this high density regime. And if you do it for 202s, you also see a shifted line, but note it's a much weaker effect now. And that's sort of counterintuitive, at least if you think about it for the first time. The big Rydberg atom contains 30,000 atoms and causes a very small effect on the condensate only, whereas the small Rydberg atom containing only 700 atoms causes a big loss. Okay. Intuitively, one would have thought the other way around, right? So if you calculate now how many atoms get lost in the 110s case, out of the 700 atoms inside, we lose about 50. And for the 202s, from the 30,000 atoms inside, we only lose 7. And that is asking for some explanation now, yes? And we come to that in a minute. Another effect that you can observe is that the whole condensate not only gets smaller, it also starts to oscillate. So the single electron basically couples to collective oscillations of the condensate, in this case a quadrupole oscillation. Here's the measurement. You just see the characteristic square root of 5/2 of omega z basically in the condensate oscillation corresponding to this mode of the quadrupole oscillation with Rydberg and without Rydberg just as a reference. By the way, you can also measure this for other orbitals, d states, and you can measure the coupling strength by just measuring the amplitude of this oscillation now. Okay. So one way to do this is to just measure the aspect ratio of the condensate after it has interacted with an electron, for example, at the maximum of this oscillation. Okay. And if you do this as a function of the detuning again, corresponding to the loss measurement up here, then you see again the 110s state, the small one, couples strongly to the mechanical oscillation, whereas the 202s basically doesn't couple at all. And that again needs to be explained. There's no mechanical effect for big atoms, large mechanical effect for small atoms. Ultimately, we have done this in a very systematic way for not only those two extreme states, but for a bunch of states in between. But basically, what we observe is that there's a gradual change from one behavior to the other. You see that this line gets weaker and weaker as we go up in principal quantum number, and also the mechanical coupling gets smaller and smaller as we go down, as we go up in principal quantum number. So now let's look at these spectra in some more detail. First thing that one can look at is this shift again, this Amaldi-Segret shift, let's call it this way. It is a slightly larger, basically, for the small Rydberg atom as compared to the large Rydberg atom. And that's the first finite size effect that we see here. If you just plot this line shift as a function of principal quantum number, Amaldi and Segre, if you have a homogeneous density, predict, actually without free parameters, because we know these scattering lengths, an independent shift, independent of principal quantum number. What we observe has a dependence on n, it's a small dependence, which can be explained now by this finite size effect. If we just take the known Thomas Fermi density distribution into account, then we see that, of course, large atoms have electrons which experience low density part of the condensate at the edges. Okay. And that actually very nicely explains our finding. And if you are interested in higher order scattering corrections in S and P wave and so on, you can see that it even more nicely explains our result, but the difference is small. So for the whole argument, really the S-wave scattering alone is more or less sufficient. Now let's come to the coupling strength to the mechanical motion and also to the explanation of why the atoms get lost. And you can explain this by formulating Bogoliubov theory in a Bose-Einstein condensate, which is what we have done in the paper. For the sake of simplicity, I just want to show you a movie that was produced by Kazik-Georgievsky and his group of this problem, where you have a condensate here, and this black dot basically describes the origin of a Rydberg atom that you are placing in the condensate. Okay, and now as the movie is going on, the Rydberg atom will leave its imprint basically in the condensate. Okay, and then after some time we excite a second one and a third one, because in the experiment we actually have a whole train of pulses in one and the same condensate. Okay, and if you watch this now, you see that the first Rydberg atom was here, and it left behind basically an imprint. First, it's a phase imprint on the condensate, but later on, it's also a density imprint that actually resembles the shape of this S-state Rydberg atom. Okay, and if you do this many times, then basically the condensate gets scrambled, it gets heated, and as a consequence, you are losing atoms into the thermal cloud. And that is what we are measuring, yes? We are measuring losses in the condensate. So, and this numerical simulation basically can be compared quantitatively to our experimental results for different principal quantum numbers and so on. And that is what they have done and put it in a plot. Here you see the number of atoms delta n lost per Rydberg atom, and I told you for 110 it's 50, for 202 it's 7. That's these black measurements points, and in between we have a smooth crossover from one to the other regime. And their numerical calculation solving Gross-Pityayevsky equation in the presence of a Rydberg atom actually reproduces this surprisingly well. Also the line shift and the full width half maximum of our curves are nicely reproduced. Okay, so this tells you now that this single Rydberg electron is basically creating a phonon wave in the condensate, which ultimately leads to losses and also to collective oscillations of the condensate. Okay, so if I summarize this, then I would say we have prepared a single electron as an impurity in the condensate, and the ionic core just serves as a trap. It's just holding the electron in its orbit. It's in a pure state, basically. And the ion itself, the interaction of the ion itself is irrelevant. The Rydberg blockade allows us to create a single one only, and we observe a strong coupling of this individual electron to the collective many-body modes, basically in a condensate, the BEC excitations. So we have started basically with an S atom. That's an artist's view. I should say I made this movie on so I'm not considering myself as an artist, but I made this movie on a flight to Japan, so I had a lot of time. So this is supposed to be an S-state atom cut in half, so it has an onion type shape here, and there's a ground state atom. And I was telling you in the beginning of the talk that at low principal quantum number, every once in a while there is one atom, and that is making these molecules. Then we have increased the principal quantum number such that hundreds of atoms are inside. Ultimately, at principal quantum number of 200, this Rydberg atom contains tens of thousands of atoms and is as large as the whole condensate itself. Okay. Now, what can we do with this now? And one thing that we are working on now is just using a BEC basically as a contrast agent to image electron distributions, pure states, for example, that are represented, of course, by the square of their wave function. Okay, so if you, for example, take S or D electrons, then they leave a different trace in the condensate. And now remember, this object here can be many micrometers large. So it is phase imprinting a structure into the condensate, which is then turning into a density distribution, which by in situ imaging techniques, state-of-the-art imaging techniques, you should be able to map out on a normal CCD camera. Okay, so that's actually what we are right now setting up. We want to observe just for fun, basically, the Rydberg wave functions. And you have seen the nice wave functions plotted in electric fields, for example, or maybe there are dynamic effects in wave functions that with this technique you can make visible, basically. Well, that's one of the things that we have in mind. The other thing that we have in mind is, what if we bring the electron completely out of the condensate, making circular atoms? Then the electron is not interacting with the condensate, but what is left behind is the ion. And of course, the ion is also a very interesting object. It has a much weaker interaction. However, the length scale of interaction is as large as the mean particle spacing. So the connected many-body physics then is the so-called Fröhlich-Polaron physics, where basically the ion is gathering ground state atoms around and create a new quasi-particle with a large effective mass. And there are two ideas. One is basically get rid of the electron by circulating it around the condensate. Actually, this has a lot in common also with nuclear physics. As you have seen, there is a quadrupole oscillation of the whole condensate, which is singly charged, and you have an electron outside. That's sort of also a fun analogy that I like, because in my faculty I have to teach nuclear physics these days. The other idea is to basically just take a very focused optical dipole trap for the ion that is left behind. And as this ion is very cold, we are creating it out of a condensate, so it's 100 nanokelvin or something like this. We should be able to trap it in a standard optical dipole trap, such that we don't need any Paul trapping, as many other people do, to create ionic impurities in quantum gases. Okay, so I maybe have still 10 minutes or so, yes. Then I would like to finish this ultra-cold experiments and just very briefly mention some of the things that we are doing, trying to bring this Rydberg physics to ambient conditions. This is our BEC apparatus where we are doing all these experiments that I just described. It's like typical apparatus, many cubic meters in size, a lot of laser systems and so on. And we really want to replace all of this by specially made microscopic glass cells containing rubidium or cesium vapor in our case. Now, of course, if you go to room temperature or even above room temperature, then the atoms start to move considerably. And if you now ask yourself, well, I mean, is this a problem? Then the answer is yes, this is a problem if you are not fast enough. So Serge was arguing that the Rabi frequencies, for example, in the typical cold atom experiment is megahertz. That is much smaller than the Doppler width in a vapor cell, and you will not be able to do some interesting, strongly correlated physics. However, if you are fast enough, which means you have to provide Rabi frequencies in the gigahertz regime to the Rydberg state, then this is larger than the Doppler width, and you can, as I will show you, enter the regime where you are sensitive to frozen gas, Rydberg-Rydberg interactions, and even many-body physics. So just, I mean, this is a back of the envelope calculation. Cold atom has maybe 1 centimeter, just order of magnitude. You have about 100 microseconds or a little less time before it moves 1 wavelength, just a rough order of magnitude. In a hot vapor, the atoms move with 100 meters per second, so you have less than 10 nanoseconds until the atoms move considerably. So you have to work on the nanosecond time scale. So we started this several years ago. People thought we are sort of crazy because the matrix element is extremely small to the Rydberg atom. As we have seen, the sizes are so different that you really have to produce, say, 1 million times more peak power than a usual CW experiment has. But this is possible, of course, if you just use a pulsed amplifier. Yes. So what we created is a 2-photon excitation laser system that produces a 4 nanosecond pulse. It has a peak intensity of 20 megawatts per square centimeter. And if you shine this peak to our vapor cell, then on the nanosecond time scale, you start to see Rabi oscillations. And we confirmed that these are Rabi oscillations by just changing the intensity of the pulse systematically and observe the typical square root behavior here. Yes, and you can compare it to simulations as well. And it nicely follows the typical 3-level dynamics. So within 4 nanoseconds at the time, that's already 2 or 3 years ago now, we were able to do 12 pi pulses during such a pulse to the Rydberg state and back in a vapor cell. So that is fast enough. It means Rabi frequencies are several gigahertz, much larger than the Doppler width. Okay. Then we were asking ourselves if we observe those Rabi oscillations. Here you see some transient signals. What is the effect of the Rydberg-Rydberg interaction? Can it be also in the gigahertz regime? Can the interaction energies also be, say, 3 orders of magnitude larger than in typical cold atom experiments? And for this, we increase the density. That's easily done by just heating the cell a little bit from like 0.1 per cubic micrometer to like 2.7 per cubic micrometer here for a principal quantum number of 37. And what you see is that these Rabi oscillations just get damped out, which is due to a dephasing mechanism that is density dependent. And if you want to confirm now that this is really Rydberg interaction, then you have to do something. You have to do systematic studies and confirm scaling laws that you expect from this van der Waals interaction between Rydberg atoms. And that's what we did. We take those plots here and basically model it with a 3-level dynamics, including a dephasing term that is only present if we have population in the Rydberg state. So that's this gamma rho 33. Okay, so that's a dephasing that is only there when the Rydberg atoms in this upper state interact. So we extract this as a fit parameter from these damped Rabi oscillations and plot now this dephasing rate for many densities and for many principal quantum numbers. Okay, so first thing you see, this is linear in density. That's how it should be. I mean, it's an interaction, a 2-body interaction effect. But then you see that, of course, the dephasing is much stronger for higher principal quantum number, like here, as compared to lower principal quantum number. And now you have to renormalize this and bring in your model of van der Waals interaction between these 2 particles. So you say, okay, there is a typical density, a critical density. This is basically this borderline that I was drawing in this overview plot, where basically the mean particle spacing becomes comparable to the blockade radius. So if you then normalize this density here to the critical density, which depends on the principal quantum number now, then all these data points fall on one plot, and you confirm basically that it is indeed a 1/R6 type of interaction that is responsible for this dephasing mechanism. Okay. And if you look at this plot now, you see that the axis here is again gigahertz, 1 gigahertz, 2 gigahertz, 3 gigahertz, much larger than the Doppler width, which is again what we need in order to look for, strong correlations, even at room temperature or above. Now, can we go beyond? I mean, this was like a weak dephasing effect. And we increased the density even further, and we didn't understand our transient signals anymore, because this is true many-body physics. It's not so easy to interpret. But there is an easier situation that you can actually access if you have a detuned laser excitation, and that is called the anti-blockade effect. So if you have a van der Waals interaction, in this case repulsive, and you detune your laser such that there is a resonant point at a certain distance, okay? This RB is then the resonant point here, yes? Then it is well known, and that has been confirmed in several experiments, for example, also by Matthias Weidemüller, who will be here next week, I guess, yes, that there is a so-called aggregate formation. That means if you have one Rydberg atom, then in a shell around it, at this distance here, there is a resonance condition, and the next one will be immediately excited, and there is a whole avalanche, basically, of Rydberg atoms forming once the first nucleation center is there. Okay. Now, there is a paper by Igor Lesanovsky describing the dynamics of such an aggregate formation. And here's a picture from his paper where you see that, okay, these red dots are Rydberg atoms. The blue circle here is basically this resonant point, yes? And you can see that as time goes on, basically the resonant volume increases with time. And therefore, you have an avalanche-type process of growth of Rydberg population in your sample. And he plots again a formula for the time constant of this aggregate formation here, which has a power law dependence on detuning, Rabi frequency, density, the C6 coefficient, and the dephasing rate as well. And so we went to our experiment and basically observe exactly this. Again, it's just a cesium cell here and a pulsed laser that we just switch on in a nanosecond and observe the transient signal here and measure this aggregate formation time tau. And I don't want to go through all these things, but I just want to tell you we have measured all these power laws, and they all coincide with the prediction of this aggregate formation. So it's density dependent, the detuning dependence is fine, the Rabi frequency dependence is measured, the density dependence, the dependence on the C6 coefficient. So all of this basically confirms that in these vapor cells we have many body physics going on now, and we get these aggregates just like people have observed them in cold samples as well. Now I'm running out of time, I guess, and I'm skipping our experiments on holocore fibers, which we can also use to excite Rydberg atoms surprisingly well and summarize this vapor cell part. So it is possible to do coherent Rydberg excitation in vapor cells on the required fast time scale. We have observed the van der Waals interaction between Rydberg atoms for a few atoms per cubic micrometer, and we have now also seen many body effects at even 2 orders of magnitude higher density, where you have 100 atoms per cubic micrometers. Yes? Now we want to use this to really build interesting quantum devices like single photon sources and so on, and fiber-based optical devices. This is what we are working on. That's not yet done, but we are, making nice progress along this direction. And finally, I just want to summarize the whole talk. In the first part, I've shown you ultra-cold experiments that are basically that showed you molecular formation in the low-density regime for a low principal quantum number. We observed trimer, tetramer polymers up to many atoms in the upper right corner where we had the condensate sitting, collective oscillations of the condensate excited by a single Rydberg atom. And in the final part, I've shown you that this kind of plot we can also explore in thermal vapor cells. The borderline here of the blockade physics is a little bit higher here, yes, because bandwidth is larger, therefore the blockade radius is smaller, so this line is a little bit further up. But we have made our way at least up to 10 to the 14 now, and still seem to understand what is going on. And with this, I thank you for your attention.